Okay, so this is part 2 of today's discussion. Before we start, I thought of something else. When I grade your video quizzes, I write comments. And I'm not sure if you're able to see my comments. I write a lot of feedback, okay? And I'm not sure if you're able to see my feedback. So if you're interested in the feedback, please check. Are you able to see it? Because I don't know, I spend a lot of time trying to explain things to students. And I'm not sure if you're seeing that. Please check. I'm trying to talk to PolyLearn support because one of the students said they cannot see the comments. And I put a lot of time into all this. Okay, so today I want to discuss why you cannot move faster than the speed of light. It's part of the big predictions of relativity. And this is related to something called causality. So what do I mean by causality? Let's say there are two events, event 1, event 2. We're used to thinking about two events by now. But these are not ordinary two events. In this case, event 1 causes event 2. What do I mean by causes? How is the fact that event 1 causes event 2 manifested? By requiring that in order for event 2 to happen, information from event 1 has to reach the time and location of event 2. So for example, I drop a rock on my foot, boom, the rock hits the foot, cause. It causes me to go, ouch. That's the effect. I don't go, ouch, as soon as the rock hits the foot. The information from my foot has to reach my brain. In this case, by means of nerve signals, which are electrical and chemical waves. And that information travels with some speed. I actually don't know how quickly information travels through nerves. It's really interesting. I think it's probably slower than the electrical disturbance through wires, but it's actually pretty fast. I'm really curious what that is. But you see, there is the speed with which information moves from the foot to the brain until I can say, ouch. So ouch and the rock hitting the foot, they are causally linked events. And events linked by information transfer are called causally linked or causally related events, okay? And in order for there to be such a thing as a cause and effect, it must not be possible to reverse the order of causally linked events by observing the whole situation unfolding, by observing this whole situation from another reference frame. Okay, you cannot find a reference frame in which I go ouch before the rock hits my foot. Otherwise, all hell breaks loose. So there has to be a constraint. There's a constraint, actually, if we think about it, related to causality. Okay, otherwise it would make no sense to talk of a cause and effect per se, because what's cause and effect in one frame is not cause and effect in another. And causality is one of those sacrilege things like principle of relativity that we just, it's our religious belief, we just want to leave it untouched. There has to be causality, right? So this idea that the order of causally linked events must be preserved in all reference frames is called causality. Okay, so this is this idea. The order of causally linked events must be preserved in all reference frames. So this is called causality. Okay. And what I mean by causally linked events, causally linked or causally related. Events are events that are linked by information transfer. Let's see if I can do this. And you see, information is transferred by some kind of a physical mechanism. Wire or sound, or throw a rock at something. There's a physical mechanism that transfers information. Okay? So I can send information at various speeds. So if I clap, boom, information reaches you. Okay, so information comes out of the speaker and boom, it hits your ear. Right? I could instead send a light pulse. I don't have a flashlight, but I could send a light pulse and then information reaches you quicker. But it still takes some time. Or I can, I guess with this method, I cannot throw a pebble, right? But you see, if we were in live, I could throw a little pebble. And that is another, it's a slower method of information transfer. You connect the slinky and yank the slinky. But the question is there the largest speed at which information can be sent? And we can make this serious, right? So if I have an electron and another electron, and they're repelling each other, but I yank this electron, it takes some time for this electron to find out about it, and react. Is there the largest speed with which this interaction is communicated, right? Interactions between particles are communicated also by information transfer. If the sun disappears, the Earth will keep going in circle for about 8 minutes until gravitational wave arrives to the Earth, and the Earth finds out there's no more sun. Okay? Interaction, gravitational interaction, it's not instantaneous. If you yank the sun, that information about the sun being yanked takes some time. Interaction, gravitational interaction between the Earth and the sun also has a lag time. Okay? So I'm asking, is there the largest speed at which information can be sent? Or is there the largest speed at which the interaction between particles can be communicated? Is there the largest velocity at which interaction can propagate from point A to point B? Okay, and the question I would like to ask now is this: what kinds of constraints does causality place on the maximal velocity of propagation of information? Very grown-up question, very mature, interesting grown-up question. So, question. This is really annoying. I don't understand why this is happening. Question. I don't understand how to get rid of this. Today, everything is going to the dogs. I mean, a lot of technology issues today. I just don't know what to do about. The question: what kind of kinds of constraints does causality place on the maximal velocity of propagation of information or interactions? Okay, that's a very mature grown-up question, and it has been answered. So I hope this is clear. I hope the setup is clear. I hope the setup of the question is clear. So here we go. Let's say there's a cause and effect. Rock falling on my foot, and I'm going, ouch. And let's say the separation between the cause and effect events is delta x. In this case, it's delta x is the distance between my foot and my brain. And let's say the time separation between them is delta t. It takes 0.1 of a second between the foot, when the rock hit the foot and when I went ouch. So it makes sense to talk about the separation between the cause and effect events. And let's say it's delta x, okay? This is effect, event. And some kind of information is traveling. And this is delta x. And there is also, you know, delta t after the cause. And let's say, so this is all in frame S. Let's say there's a frame S prime. It's moving with some velocity relative to frame S. And I'm observing the same scenario from the frame S prime. Now, let's say, and I want to know, is it possible, I'm going to try to push it to extreme, is it possible to reverse the order of events? Okay. Now, let's say the information from cause to effect moves at the largest speed possible. I'm going to call it U star. Largest speed possible. So I can send information by yanking a slinky, slow. I can send information by sending a snail, even slower. I can send a sound pulse, not bad, pretty fast. I can send a light pulse, even faster. Let's say there exists a mechanism of information transfer, which is the fastest, okay? So that's U star. So then what's the relationship between delta x and delta t? Well, delta x equals U star delta t. Or delta t happened, or delta t is delta x over U star. In other words, the effect took place this much later after the cause. So far, so good. So let's say I'm observing the whole craziness unfold from sitting, you know, in my chair while moving in a spaceship, now a proverbial spaceship or a train. I'm just looking at all these things, and I'm timing the events between cause and effect. Okay, so I say, delta t prime equals, according to Lorentz transformation, it's delta t times gamma v times 1 minus v over c squared delta x over delta t. This might look a little bit strange to you, but I just factored out delta t. Now delta x over delta t is U star, so I can say that this is delta t times gamma v 1 minus U star times v over c squared. So here's the kicker. If we insist on preserving the order of cause and effect in all frames, then it must be true that this darn thing has to be positive. Okay, must be positive, greater than 0, if we insist on preserving the order, i.e., that the sign of delta t prime and delta t signs are the same. If delta t is positive, hey, delta t prime is better be positive too. If delta t is negative, fine, but delta t prime is better be negative too. And it should be impossible to make it positive. It should be impossible to flip the order of causally linked events. Now, this statement is that it must be true for any v, for any reference frame. Well, let's look at this. First of all, it's automatically true if v is negative. If v is larger than 0, imagine I start turning up v. So I'm moving in successfully faster and faster frames s prime. This term right here is becoming larger and larger, and so the whole thing is getting closer and closer to 0. So if v is larger than 0, as v gets larger and larger, this quantity gets smaller and smaller and closer to 0, and so closer and closer to going negative, which we don't want. So as v gets larger, this factor gets closer and closer to flipping sign. However, by definition of u star, it makes no sense for v to be bigger than u star. Okay, so v has to be, so note, less than u star. Because agree, by definition, u star is the maximal velocity of propagation of information. So if v was bigger than u star, well, that evidently I can move information from the cause event to the effect event by dropping a package into something that's moving faster than u star, and it would be, and then u star is just not u star anymore. It's not the fastest speed of propagation of information. Okay, so v must be less than u star just by definition of u star, or equal to u star. Okay, so v is less than or equal to u star. So again, u star, in order to be maximal velocity of propagation of information, has to be bigger than or equal to v, because otherwise I could drop a package into frame s prime and it will arrive to the effect location faster than the signal moving at u star, which means that information could travel faster than u star, which contradicts what u star is. So this is not deep. This is just by definition. By definition of what u star is. So therefore, a little bit of math, u star times v is always less than u star squared. 5 times 3 is less than 5 squared. 5 times 4 is less than 5 squared. 5 times 4.9 is less than 5 squared. So the smallest that 1 minus v, what is it? 1 minus u star v over c squared can be is 1 minus u star quantity squared over c. And we want that to be bigger than 0. The smallest that this factor could be, if I keep pushing, well, okay, this. And that has to be bigger than 0. 1 minus u star squared over c bigger than 0. A bit of math, which voila, says that u star has to be less than or equal to c. So what we have found, this is a big deal. Okay? So what we have found is that causality is what requires that maximal velocity of propagation of information be less than or equal to c. It's equal to c if you're propagating information with something that moves with speed of light. That's a big deal now, okay? So causality says maximal. Okay. Note that this conclusion is dependent of a frame, is independent of the frame. It must be true in all frames. So the more commonly stated that you can't move faster than light is less accurate. But it's correct as long as that's equivalent to moving information. Now, here's a little bit of a pep talk. Look, special relativity is not a theory of light. It's not a theory of light. It's a theory of how space and time are related. As we see, special relativity turns out to have very far-reaching consequences, including that it imposes a speed limit on which information can propagate. There are other interactions, for example, gravitational, that have nothing to do with light per se. There's a strong force, weak force. There are other types of fundamental interactions, not just electromagnetic interactions. So it would be more appropriate to call c not the speed of light, but the maximal velocity of propagation of information. Okay? And light as a phenomena happens to move with that velocity. And then a different statement of the second postulate of special relativity would be that there exists a maximal velocity of propagation of information in all frames. And that's actually how it's sometimes stated in the modern interpretation. And that makes it clear that relativity is not about light. Okay, another name could be, another name for C could be maximal velocity of propagation of interactions. And there are many types of interactions: gravitational, electromagnetic, strong, weak. Light is simply a method by which charges interact, and it happens to have that maximal possible velocity. The method by which charges interact happens to be that very maximal velocity of propagation of information. So maybe historically it's called speed of light, but it really should be called speed of the maximal speed with which interactions can propagate. And it's actually not obvious that this has to be the case. You can imagine a universe in which interactions propagate instantaneously. We happen to live in a universe in which there's a maximal speed limit on how fast interactions can propagate.